In this video, we're going to take a look at optimization with linear programming. Sounds pretty fancy, but the general idea is we are going to apply these inequalities we've been graphing. So we have already graphed inequalities using either solid boundary lines if we can equal the line, or dashed if we cannot equal the boundary line. And what we're going to look at is some different situations where we have something called constraints. So, in terms of production of items, we might have a limit to how many items we can make, or we might have a minimum goal we need to reach. So, we'll practice writing inequalities to represent these goals and boundaries that we have. And what we're going to look for is something called the feasible region, which is going to be a region that's shaded by all of our inequalities. And this region is going to represent values that are practical to our scenario. So we're going to take a look real soon at an example of this in terms of making cookies. And so in a bakery. And so we'll see all the possibilities that this bakery has for their constraints, and we'll talk about what values are feasible to the situation and which ones are not. And it's all going to be based on the inequalities we make. So as any application goes, the first thing we should always do is write variables. Since we are graphing, it's going to be a good idea to use X's and Y's. And we'll then use these two variables as we write our inequalities as they're described in the scenario. We don't really know how many inequalities we're going to need. It's going to differ from one situation to the next. And it can be kind of difficult to figure out how many you're going to need. So don't panic about that. We're going to always kind of help you out to know how many are needed and give you some guidance along the way. So we're really just going to get an introduction to how all this can work. We're not just going to expect you to be able to do it all on your own from the get-go. So then once we have all of our inequalities, just like normal, like we had before, we'll graph them with either solid lines or dashed lines. And then we should end up seeing the feasible region appear, and it's going to be this region that's shaded by our boundary lines. And then what we're going to do is we're going to talk about within this region, how can we maximize or minimize a certain amount. So sometimes we want to maximize values like profit, since profit is money that we are making and keeping. So as far as a business goes, you'd want to make as much money as possible. But maybe we want to minimize values such as cost. So the same idea with a business. It's going to cost you to purchase materials to make your product. You would want to maybe keep that cost as low as possible. So maybe we'll maximize or minimize. That'll be a case-by-case basis. And that expression is always going to involve dollar amounts. So when we talk about maximizing and minimizing, we're talking about money. So what we're doing today is very common if we want to talk about a business model. So maybe that expression is an example of 3x plus 4y. So this would be $3 per x, $4 per y. We would know what x and y are because we defined them earlier. And then what we're going to do is we're going to use the corners of our feasible region, the shaded region that's going to appear. A vertex is a corner point. And again, we're going to hint to you how many corner points your shaded area should have based on the number of rows that we're giving you to fill in. So again, this is an introduction, and we are not expecting too much from you at this point, just basics, just getting into the basics of how this can work. Okay, and using these vertices is going to be pretty simple, and you'll see this in our example in just a moment. All we have to do is we have to take these corner points from our graph, we'll substitute into our expression that involves money, and we'll see what the end result is. And so if we're trying to maximize, we'll look for the highest result possible. If we're trying to minimize a value, we'll look for the lowest result possible. And since we are doing this and it's kind of like creating a report at this point. We will specify what values gave us the highest and lowest results. And then in any application, when we provide solutions, we don't just write down numbers. We respond back in words that appropriately address the question within the scenario. And so that'd be the last thing we'll do, and use full sentences. You probably won't be writing more than 1 or 2 sentences in any of these situations. All right, so let's take a look at one of these examples. So this example here, it's about the cookie factory. Not necessarily a real place, but there's probably somewhere that's called that. This scenario is a little wordy. The things that we'll do in our assignment are going to be a little more straightforward. But let's talk about this one, and if it's a little more complicated than what we do later, then that's fine. We're getting the more complex scenario out of the way. So here's what we know about the cookie factory. Their best-selling items are chocolate chip and peanut butter cookies. And what they want to do is they want to sell both types of cookies together in a combo pack. And they have a sales plan outlined down here. So they're going to create these combo packs that might have a variety of these 2 types of popular cookies. Here's some constraints they're giving. They want each package to contain at least 3 of each type of cookie. So we know that the combo pack will be guaranteed to have 3 chocolate chip and 3 peanut butter cookies or more. So that is that's a couple of constraints we're seeing already. We will have at least 3 chocolate chip and 3 peanut butter cookies in a pack. Okay, we also see the different size packages must contain at least 6, but no more than 12. So in these combo packs, they want a minimum of 6, which makes sense because we'll have at least 3 chocolate chip and 3 peanut butter. But they don't want to do combo packs of more than 12 cookies. So there's another constraint. No combo packs can go beyond 12 cookies. Okay, so let's see what it says in C. The cost of making a chocolate chip cookie is 19 cents, and the selling price is 44 cents. So if we know the cost of making the cookie and we know how much they're selling the cookie for, we should be able to calculate how much profit they're making off of each cookie. All we need to take is 44 cents minus 19 cents, and we are going to see that is 25 cents per cookie, per chocolate chip cookie. So 25 cents for each chocolate chip cookie. That will be their profit that they're making. And just like with the chocolate chip, they'll also make profit off their peanut butter cookies. Based on this information, the cost of making a peanut butter cookie is only 13 cents. So they're going to sell these cookies for 39 cents, meaning that their profit for these cookies is 26 cents per cookie. So they'll make a 26-cent profit for each peanut butter cookie. So now we know the profits of each one. Okay, so what we need to do is define our variables that are being described in this scenario, and maybe you've kind of figured out what we've been discussing in this. We're going to be making combo packs that contain chocolate chip cookies and also peanut butter cookies, but we don't know how many chocolate chip and how many peanut butter cookies will be used in a combo pack. And if we don't know exactly how many of each type of cookie will be included, then we'll use variables to represent those unknown values. So we're going to be making a graph here. And because of that, we'll use the letters X and Y for our variables. So let's use X and Y here, and it doesn't matter which type of cookie you use for which variable. Let's just decide to use chocolate chip with our X variable. And so what it is that we don't know about is how many chocolate chip cookies we'll use. So we can just, very simply word that as let X represent the number of chocolate chip cookies. And Y can be our number of peanut butter cookies. So number of peanut butter. Here we go. All right, so what we need is constraints, and here we go. I'm tipping you off already. We've told you how many constraints there are altogether. So there are 4 limitations or 4 goals that we need to meet in terms of these combo packs that are going to be made with the Cookie Factory. So let's see what kind of goals or limitations there are. So let's go back to the beginning. In here, their business plan, they said they want each package to contain at least 3 of each type of cookie. So that means at least 3 chocolate chip cookies. There's one constraint. We have to include at least 3 chocolate chip cookies. And we're using X to represent our number of chocolate chip cookies. So an inequality for that would say X, your number of chocolate chip cookies, has to be greater than or equal to 3. Okay, so we'll have at least 3 chocolate chip cookies, and we're supposed to have at least 3 peanut butter cookies. So just like we did with X, we'll do the same with Y. We need at least 3 peanut butter cookies. Okay, there are 2 separate inequalities, so that is 2 of our 4 total constraints. And if you read up top, you see that there's a couple more values being described up here in part B of the sales plan. Those are representing a couple more constraints that we have. So this is saying that your combo pack must contain at least 6 cookies. Okay, so in other words, your combination of peanut butter and chocolate chip cookies should at least be 6. Okay, so our constraint for that one is simply going to be X plus Y, your number of peanut butter. Fix that. Okay, X plus Y, your number of chocolate chip combined with your number of peanut butter, should be at least 6 total cookies. And we also see that combo packs will not contain more than 12 cookies. So there's another limitation. We will not have more than 12 cookies in the combo packs. So your number of chocolate chip and your number of peanut butter cookies within those combo packs, that amount cannot go beyond 12. So it either needs needs to be less than 12 or equal to 12. So we'll use that less than or equal to sign. And there you see we have 1, 2, 3, 4 inequalities. So there are the 4 constraints that we needed. Okay, so we got those from parts A and B of the sales plan. All right, so now that we have these inequalities, what we need to do is graph them. So let's take a look at what these graphs look like. You notice there are parts of this graph already prepared for you. We have blanks for labels because if we are making a business model or if we're displaying a business model, when we present a graph, anybody should be able to look at the graph and know what it's representing. So we have places for labels. We'll get those. We've defined X and Y, and so you should label your axes the same way. For the X-axis, we'll put what X was representing. So down here, this would be your number of chocolate chip cookies. Okay, and for the Y-axis, we have our number of peanut butter cookies. Normally I can turn my paper sideways, and I'm going to do my best to write it sideways here. So number of peanut butter, I'm going to abbreviate peanut butter cookies. Okay, that wasn't so bad. So now we know what the graph is going to show us. Now you might notice in the graph, I've shown quadrant 1, okay, because we have the x-axis on the bottom row and the y-axis on the far left column. So I'm showing this quadrant that only has positive values, which is what we want because we do not plan on making negative chocolate chip cookies or negative peanut butter cookies. It wouldn't really make sense. So we don't need to show any negative values because they would not make sense for the situation we're working in. Okay, so what we need to do is we need to graph these 4 inequalities in this grid. If you have colored pencils, this might be a good time to do that. or pens or markers, something, so that you can see the 4 separate lines that we're about to graph. But let's start with this one that says x is greater than or equal to 3. It only uses the letter x. It should only have an x-intercept. So if you recall, when we only use the letter x, that is a vertical line. And since we are able to equal the line, we will make a solid vertical line at x equals 3. So let's see if we have room here. I believe none of these numbers look too large to me, so it looks like we can count by ones. So I'll just show that really quickly so that anybody that looks at my graph knows what my scale is. We're counting by ones. So a vertical line at x equals 3 is going to be right here, and it is a solid boundary line. Okay. And it would keep on going, but we're just going to look at this part of the graph right now. Okay, so we have not shaded it yet, but if we did, this says x is greater than or equal to 3. Well, x values that are greater than 3 would be in this direction. So I'll just keep track. When I shade for this one, we should be shading to the right. Okay, but you'll see in a moment, we'll know where to shade in the end, most likely. So just hold tight. Let's try another one of these. We have another constraint that says y is greater than or equal to 3. Well, when we just use the letter y, that would be a horizontal line. So we're going to have a solid line because we can equal, and the solid line is going to be horizontal at a y value of 3, so that would be going this way. So let's draw this horizontal line across. And actually, maybe I should keep track of what I'm doing. This is the line y equals 3. Y is greater than 3, the inequality would require me to shade, and greater than 3 would be above this line. So for this one, I'll end up shading above it. And I'm going to go ahead and label that vertical line we had. This would be the line x equals 3. And because we had the constraint greater than or equal to, we'll shade in this direction. Okay, so there's 2 of our 4. We do need to graph this line here, and that is what this space underneath is for. When we graph, we like that slope-intercept form where y is by itself. So here's x plus y is greater than or equal to 6. Let's just leave it, well, no, we can do this. So greater than or equal to 6, let's subtract x on each side to get y by itself. And we'll have y is greater than or equal to negative x plus 6. Remember, we cannot combine these terms because they do not have, both have the variable x. But we should be able to graph this one. Now that it's in slope-intercept form with y by itself, we see we have a slope of negative 1, which we could write in, and we have a y-intercept of 6. So if we count up to 6, there's our y-intercept. Here's our slope of negative 1, which would have us go down 1 unit to the right 1 unit, so a decreasing slope. And then we can repeat that process. Okay, so just kind of placing dots to guide my line through the grid. It's a solid line again because we can be equal to it. So what we need to do is just draw a slanted line here through our points. And maybe you've thought of it this way, maybe you haven't. It says y is greater than. That means your y values are going to be greater than your line. And so if your line is this orange line here, y values that are greater than this orange line are going to be above it. So this orange line is going to end up making us shade upward. All right, so we have 3 of our 4 lines. We have one more, this x plus y is less than or equal to 12. Let me pick a new color here. We'll go with red on this one. Let's take this inequality, x plus y is less than or equal to 12. Let's isolate the variable y. Same idea, subtract x to cancel over here, and we have y is less than or equal to, and we have negative x plus 12. So just kind of like last time, we have slope-intercept form. Our y-intercept this time is 12, so we count up to there. This was 6, so 7, 8, 9, 10, 11, 12. Slope is negative 1 again, so we go down 1 to the right 1, down 1 to the right 1, and continue that pattern. And I think what you're going to notice is in all the scenarios we gave you, since this is a introduction to this process, you're going to see that these lines end up crossing each other. And when they do that, don't be surprised that they are going to cross each other at the corners of these unit squares. So when the red line just crossed the green line, it was at the corner of a box. And when we cross this blue line, it's also at the corner of a box. Okay, so there's our fourth and final line. It says y is less than or equal to. So that would be shading in this direction below it, because y values that are less than this red line would be down. So you could really try to figure this out. We only want to shade one area of this grid, and this area is going to be a geometric shape typically, and it's going to be the area that is only shaded by all four of our lines. And you could take a long time trying to figure that out. We've gone through it already. We said we're going to shade to the right of the green and above the blue, above the orange, below the red. But if you just go and look for the area that is contained between all of your lines, then you're going to find that area. And you should notice that that is right here. If we look inside this area, if we look here, there is a triangular shape, and this triangle is bordered by the red line, it's bordered by the blue line, it's bordered by the green line, and it also just barely includes this orange line. And this is the only area on this graph that contains all of these lines that we graphed. So this is what we call the feasible region, and this is where we shade. Okay, so I'm going to shade this area, this triangular area. And just kind of remind you, that's called the feasible region. And feasible is that word that's practical, it's possible. These are values that make sense. And when we think of it in terms of our cookies again, it'll make more sense to us. So that is our feasible region. We're going to use it in just a moment. Okay, but the idea here is any of these shaded points are possible in our scenario. Any point we pick within this area contains a number of cookies that we could use in the combo pack. But what we're going to figure out is which combination of cookies is going to maximize our profit. Okay, so that is where we're going now. We have this next step that talks about expression. And when we talk about the expression, we're talking about an expression for money to either maximize or minimize. And in this case, we are trying to maximize an amount. We are trying to maximize profit. Okay, so my expression then to maximize profit, let's look up top. We need to remember how much our profit is for each cookie. And that's what we did in parts C and D. The profit for a chocolate chip cookie is 25 cents. The profit for a peanut butter cookie, 26 cents. Okay, so our expression, very simply, to show 25 cents per chocolate chip cookie, we just put that 0.25 as our coefficient for x. And if you want to put dollar signs here, that's fine. And then we'll combine that with our profit from peanut butter cookies. And if that's 26 cents per peanut butter cookie, we will put 26.26 times y. We'll use that 26 cents as the coefficient. And that's what we mean by the expression. This expression here will calculate our profit for combinations of chocolate chip and peanut butter cookies, which is what we want to maximize. Okay, and that's what we want to include right here. The expression, we're going to use exactly what we put in step 4. So this is just an organizational process. We found our expression. What we're about to do is we're going to use it. So I'm going to put that 0.25x plus the 0.26y. Okay, I'm just saving space by not writing that dollar sign down. And what we need is we need a vertex, and actually we need a few. And you notice that we have 1, 2, 3 blanks. That was kind of the hint that the feasible region, the area that you shaded, should have had 3 corners to it because a vertex is a corner point. Okay, so lucky us, I believe we did that because you look up here and we see that we shaded a triangle, and triangles would have 3 corner points. And what we need to know is where those corners are located. So if we look up here, here's one corner point, and it looks like that point is located at 3. Let's count up. Here's 3, 4, 5, 6, 7, 8, 9. So this is the point 3, 9, and that is the first vertex that we can put in here. It didn't have to be the first one, it's just the first one I looked at. So here's our vertex 3, 9. Let's go find the others. We have a vertex down here at 3, 3. And we have a third vertex way over on the other side. This corner point, I believe, is at 9, 3, but let's double check. So here's 3, 4, 5, 6, 7, 8, 9, and up 3. So the last vertex is located at 9, 3. And it just so happens that these all use 9s and 3s. That's just coincidence. Not all scenarios are going to do that. Okay, so there are the 3 vertices. We have our 3 corner points. What we're going to do now is we're going to take our x values that are always listed first. So we'll take our x values, replace them here, multiply them with 25 cents. Take our y values, put them here, and multiply them with the 26 cents. And we're going to see which combination of cookies here is going to maximize our profits. So let's start with the first one. We see that this first one says 3, 9. That means this would be a combo pack that contains 3 chocolate chip cookies and 9 peanut butter cookies. So if we wanted to calculate how much profit that is, that would be 25 cents times 3 plus 26 cents times 9. Okay, and then grab your calculators really quickly. And we should end up seeing that that would be a profit of $3.09 per combo pack sold. So if we have a combo pack that has 3 chocolate chip cookies and 9 peanut butter cookies, that's how much profit we'd make off of each box sold. Okay, so we try this again with another vertex to see what happens. So this combo pack would be for a package that contains 3 chocolate chip and 3 peanut butter. So we can take the 0.25 times 3 and also the 0.26 times 3. Grab our calculator, and we see the overall profit here is $1.53, which we shouldn't be surprised. This combo pack has fewer cookies than this one, and it contained the same amount of chocolate chips. So we're not surprised that this smaller combo pack has a smaller profit than the one from before. But you might notice that the last combo pack also has 12 cookies, just like the first one did. So which combination of 12 cookies creates the most profit? We will find that out as soon as we put our values into the expression. We have 25 cents times 9 this time, plus 26 cents times 3. calculate this, and we see that this is $3.03 per combination pack, which is just slightly less than the other. And again, not totally surprising because we have 25 cents and 26 cents in our expression. This top one multiplied the bigger number by 9, while the bottom multiplied the lower number by 9. So what we see is that this right here was the overall highest result. And that's what the vertices are for. Each vertex is a corner point, and those points are where either the highest value or lowest value occurs. We can have combo packs that have different amounts. So we could do, for example, we could have a package that has five peanut butter and 5 chocolate chip cookies. But this point, while it's possible, while it's feasible, is not going to be a point that creates our maximum or minimum profit. And that's what we're looking for, how to create a maximum profit. Okay, but now that we've gone through and we've figured all of that out, we're just going to explain what we saw. So these last 2 steps, very brief here, okay? We're just summarizing our report. We're going to describe the maximum and minimum amounts that occurred. And let's just be very algebraic about this. We'll just talk about when we saw a maximum. So we can just say we saw a max of $3.09 at the vertex 3, 9. And then underneath that, we can say where the minimum occurred. We can say the minimum of minimum amount was $1.53. So the minimum profit that can be made with our constraints is $1.53. And that was at the point 3, 3. So we saw that's what optimization does. It finds the maximum and minimum. We've done that. And now that when we get to the answer, we just think through what was the overall question that we had. And that was simply, how can the cookie factory maximize the profit? Well, that's what this result is for. Okay, this one describes how to maximize the profit. And so that is the last thing we'll say. The cookie factory can maximize the profit of combo packs the profit on combo packs by including what was it? It was 3 chocolate chip cookies. So 3 chocolate chip and 9 peanut butter cookies. And that is not the only way you could write all of this by any means. There could have been a more efficient way to go about that, but it does state all the information that we needed, and that's what we needed to include. We needed to include the idea of maximizing the profit and how many cookies that would take. So I guess even further, if we wanted to, we could include how much that profit was. So maybe we include the cookie factory can maximize the profit. We could have said the cookie factory can achieve a maximum profit of $3.09 with combo packs including 3 chocolate chip and 9 peanut butter cookies. And so here's just one other way that we could write this, and there are lots of ways to do this. I'll probably write it a different way every time I do it, but including that important information of maximum profit, even better, including how much that maximum profit is, so $3.09, and then explaining how that's achieved. What was the 3 for? What was the 9 for? 3 was our X value, so 3 chocolate chip cookies and 9 peanut butter cookies in that combo pack. I hope you can use this as an example, help you along with the other applications. Again, helpful hints along the way will always let you know how many constraints there are and how many corner points your feasible region should have. Good luck.